Okay. Okay, we're going to wrap up talking about composites today. So I'm going to introduce you to these bubble charts of materials properties. They're becoming more and more prevalent, at least in my field, so you might see them again someday. Basically, it's a way of thinking of if you material can have, you can compare properties by looking at them in two dimensions on this graph. So here we have Young's modulus and density. And so this is obviously, an important consideration. These are two properties that are important for things where we want something to be stiff and light at the same time. So that's going to happen, situations like the outside skin of the airplane, or panels or I-beams that we need for light buildings. So what we see is this here, these lighter bubbles. So this is the polymer matrix. Those are polymers, kind of sit in that bubble of properties. They have that range of moduli here, all below 10, so not very stiff at all, but low densities. So less than, around 1 to 2 grams per cubic centimeter. And then in here we have all the metals. Much, much stiffer, a couple orders of magnitude stiffer. So we measure, again, metals moduli in hundreds of gigapascals. And then, but much denser, so farther over that way. What we see is if we were going to plot the ceramics would all be in here somewhere. Technical ceramics like silicon carbide, diamonds, alumina, things that we use for their insulating properties, technical ceramics, and then cement and brick and things are over in here, or not there. I'm actually not sure where those are. Somewhere around there too. Much denser. And so, so there's a number of these ceramics, carbon fibers that are light and stiff, but of course they're then brittle. But when we combine, the polymer matrix with the ceramic properties up here, we end up, again, somewhere in the middle. And we talked about that, where the properties of the composite are going to be some combination of the properties of the matrix and the reinforcement phase. And similarly with metals. And this is the reason we do that. Because if we're thinking of modulus versus density, where on this graph do we want to end up? Where do we want our properties to be? Yeah, up in this quadrant. Here's the sweet, that's where we want to be. And so composites allow us to move in that direction in terms of the materials we have available and what properties they have. Same thing with strength versus density with metal and polymer composites. Okay, so here's a quick question. We have an aligned fiber reinforced composite. What's it going to be? So the fibers are aligned. They're fibers. Okay, right, anisotropy. Anisotropy is where the properties are, only about 60% of the class here. Because it's so nice out, right? Okay, so anisotropy. So just a quick review of what we talked about on Wednesday. If we have these fibers aligned in one direction, then the properties are going to be very anisotropic. They're going to be different in one direction than in the other. So what we talked about is the best we can get is if we have these long fibers we orient them in a certain direction in the matrix, and then we load longitudinally. And the derivation for these, we call these rule of mixtures. Rules of mixtures. And the derivations for them are here. But, you know, we're basically saying that the strain is the same in the fiber as in the matrix. Just like if we're pulling the two springs apart, then they're going to go apart the same amount. So what we use these equations for, this is why this is important. What do these equations tell us? They tell us that if we have properties of the matrix phase, which we can determine, okay? So we can determine certain properties of the matrix, or we already know them, you know, we can determine them with tensile tests and things like that. Then we can say the best case scenario for a reinforced, fiber reinforced composite, we can calculate the best case scenario, whether or not we even have a chance of getting the properties we want with a certain matrix phase, a certain reinforcement phase, at a certain volume fraction of reinforcement. That's why these are valuable. So these are the equations, these and then the ones for particle reinforcement that you're using on the homework. And these are really the only equations that come out of the composites unit. And this is why they're important. Because you can actually go, you know, as a material scientist or as somebody who's using materials and say, okay, well, what if we were to design a new composite? Or what if we were to increase the volume fraction? How much might that get us in terms of improvement in properties? So what do all these variables mean? So obviously E of the composite, E of the matrix, and E of the fiber. So it's pretty straightforward for stiffness. You know, just this rule of mixtures of weighted average on the stiffness. With the composite strength, things are a little bit different in that the stress, so let's talk about what happens for failure strengths, failure stresses in a composite. The composite is going to fail at some point when the fiber fails, okay? So, and fiber failure can mean that the fiber's breaking, you know. It could mean, you know, that the fiber's just pulling away from the matrix, so it's not taking any of the load anymore. There's no way for the matrix to distribute that load to the fiber. Either of those will mean failure for the composite. And so that's what this here. So failure in the composite, it's going to relate to something about the stress that the failure that the fiber can take. Now, here's the point that I would make. Sorry, I missed it. That's going to be the stress in the matrix when the fiber breaks. This is the failure strength of the fiber. Okay, so these stars mean they're the actual properties of the material. So the failure strength of the composite is the volume fraction of the fiber times the strength of the fiber. But the strength of the matrix is not what's important. What's important is the stress in the matrix when the fiber breaks. So it's this new term. This is the stress in the matrix, right, that's written there. So the stress in the matrix when the fiber fails. So we're not talking about the yield strength or the tensile strength of the matrix itself. We're talking about a different property for strength. And so thinking about what the strength might be is a little bit less straightforward, but we can definitely get, the max possible stiffness. So we're going to use those in a few minutes. Well, I just put those on there. So basically, these are the equations we want. So this is for the best case scenario. Now, we're not always going to have that longitudinal orientation, right? So this aligned orientation, so this is the best. We could have some randomness in 2 or 3 dimensions. Okay, so think about when we're making these things, the 3 different ways we can get it. So here, for k equals 1, that was the rule of mixtures equation. Okay, so here's a modified rule of mixtures with this k, this efficiency factor, which basically says how efficiently are we using those fibers. Most efficient, right here. Okay? So now if we were aligned perpendicular in the plane, remember we said that was kind of the worst case if we were going this way, and we're pulling on it that way, then the fibers aren't really adding anything. That's the assumption. I mean, it's close enough to 0, basically. That really when things are stressing, so it's the matrix. The matrix is there and makes the stuff. The other 2 that are interesting is this one, this random oriented within the plane. And this is pretty common, where we'll take these carbon fibers and lay them in the epoxy and do layers of epoxy. Okay, so, within a layer, they'll be all over the place. And then we'll, maybe do several layers like this. But so in this direction, we have randomness. And so then this k value is 3/8 along that line. If it's random in 3 dimensions, and the reason it's higher here is because we have, the fibers are all randomly, but they're still all flat on that surface. So we're still, if we're getting them, pulling them along their length. If they're random in 3D, then you can imagine, we've got a lot more situations where I'm closer to having the fiber. More frequently, the fiber is going to be oriented such that the stress is kind of just, it's not loading on the fiber, so it's more frequent. And I don't think that comes up in your homework, but it doesn't come in your homework that you need these k values, but this is this other way of aligning the composites. This is a very common situation. You can think of it as a little less than half as good as if we had them oriented. Just a good rule of thumb that those sandwiched panels, it'll come back to me. Okay, here's another question. So let's see if you got all of that I just said. It didn't come out as clear as I wanted it to. Oh no. Okay. That's not going to work. So, increasing strength in the transverse direction. So let's talk vocabulary here. Increasing strength we get. Which direction is transverse? Oh. So before, I didn't have the whole transverse direction. I had these so I updated some of the images on my slides and forgot about that. Okay. So in the transverse direction, which one's going to be the best? C. This is now the strongest in the transverse direction. So again, always thinking about, when you think about using these And so here's something that came up in one of the classes I was teaching yesterday in the material science department. So we're looking at, having them look at different properties of different materials, okay? And they were supposed to tell me, something about which one had the best of these, which had the best trade-off between strength and density and met with these certain criteria. And a lot of students just put CFRP. And they got the question wrong. Why? They just put carbon fiber reinforced polymers. Why might I not give them credit for that? Again, this is their major, so I have to be a little bit more considerate. What else matters? Right. The direction, right? So they were looking at certain things, and the answer was actually epoxy matrix. So CFRP is a general thing. Carbon fiber reinforced polymers. So we don't actually know which polymer it was. So I didn't know they didn't tell me what the matrix was, and they didn't tell me how the fibers were oriented. Continuous fibers, oriented longitudinally, all of that matters. So when you're going out and just considering, even just buying a polymer, product, like all of this matters. So let's talk about that a little bit. So this is one of the questions from the homework. We want to form an aligned and continuous. Aligned and continuous fiber reinforced epoxy composite. We have a maximum of 50% volume of the fibers. And we have these certain things that we need to make sure happen for our composite. The E has to be greater than or equal to 50 gigapascals. And the tensile strength has to be greater than or equal to 1,300 megapascals. So the question that comes up when you're attempting this homework is, if you look in the back of your text for this chapter, there's like 8 different equations that all have the same values, the same variables in them. They all have E of the fiber, E of the matrix, E of the composite, failure stress of the fiber, failure stress of the composite, stress in the matrix when the fiber fails. They all have volume fraction of the matrix or volume fraction of the fiber, which are just related by that's equal to 1 minus VF. They all have the same exact variables in them. So which one do you use? So you first ask yourself, are we continuous or discontinuous? Discontinuous is a little weird. We don't usually deal with it much in this class. But what it means is that those fibers aren't long enough. They aren't 15 times the critical length. So they're short fibers, whiskers. And we treat those a lot like particles. So discontinuous would be whiskers. Isn't that a great name? We're so creative. Okay, are they continuous or discontinuous? Then, are they aligned, random, and so we're continuous and aligned, and then where's the stress? Is it transverse? Actually, I'll do it. Longitudinal or transverse? We're actually not told whether it's longitudinal or transverse. What do you guys think based on the problem statement? Who says longitudinal? Who says transverse? Okay. longitudinal because we're trying to get the maximum. Oh, well, that's the modulus listed. Yeah. I was actually coming down because we're trying to find, is it even possible to get it with these? Okay. So then that tells you which equation to use. Does that make sense? So when you look at the equations, when you're reading the section in the book, each equation is for a different situation. And so the equation for the modulus, again, of the composite, is volume fraction of the matrix, E of the matrix, plus volume fraction of the fiber, E of the fiber. So the question then becomes, which of these could work? And so you're given, like, I think one is a glass fiber, one is a carbon fiber, and one is an aramid. Anybody know what that means? We didn't talk about this in polymers. Anybody familiar with that material? What's another really strong fiber we use in bulletproof vests? Kevlar. So aramids are Kevlar. They're very strong. Or Kevlar is an aramid. And they're polymer chains that are just very, not polymer, polymers fibers that are very, very strong. And so basically, your question becomes, do we meet the modulus? What was it? Is the modulus greater than 50? And then do we meet the yield stress? Requirement. So that's the process. And so when you're looking at these questions on the homework about, well, which equation do I use? Go through and say, okay, are we continuous or whiskers? If we're fiber. Are we aligned or not? And then, what's the loading direction? Okay, so let's watch a couple of really fun videos. Well, moderately fun anyway.
To the main guy, this is just a bicycle. Its handlebar support is made of carbon fibre. Carbon fibre is a relatively new, sophisticated material that has found many uses in the world of sport. Tennis rackets, skis, hygienic bottles. It's light and supple, yet strong, boosting performances. The weaving varies according to use, giving the object strength and flexibility suitable for its function. Carbon fibre is made up of complex design of rigid fibre strands that are bathed in epoxy resin, giving it its surprising characteristics. In each strand, there are between 3,000 and 12,000 carbon fibres, all tightly packed together. Here, several strands have been broken so that we can see the end of each fibre. Long grooves, some of them very deep, scar the surface of the fibres. When the material is bathed in resin, these grooves act as anchor points for the resin, ensuring maximum cohesion. On the side of the fibres, a few fragments, the result of natural breaks in the strands, stay attached. The cut surface of the fibre appears uneven. This rough surface indicates we're approaching the deep interior of the material. the heart of carbon fibre now is. In the middle of the screen is a stack of carbon ribbons of all sizes and densities, giving the surface a disorganized appearance. The ribbons are long strands of carbon atoms. We can see them stacked up on the lower half of the screen and assembling parallel lines. In the center of the screen are the same ribbons of carbon atoms, yet lying in another direction and seen from above. A perfectly organized beehive of carbon atoms.
Okay, so the point I would want you to see from that one, you see like they purposely engineer a lot of these fibers so that they're rough. You think of that, on the macro scale, we do that sometimes too, so that we adhere in the polymer matrix. Okay, this one's shorter. Okay, so the sound isn't as cool with this one, but basically they're compressing, doing a bend test on a carbon fiber I-beam. And so it's taking a ton of stress. Can't even break the darn thing. It has to it's so flexible. Okay. So I wanted to show you those. I've got some other videos I can post as well about, another thing that they use a lot of carbon fiber reinforced polymers for is like aircraft's fuselage, the outside skin of the aircraft because of these properties. Okay, so we've talked about, for spheroidite steel is kind of like a particle reinforcement. Or the tempered martensite have the same kind of structure but much finer. That's kind of like a particle reinforcement. So particle reinforcements are similar to, fibers loaded in the transverse direction. Okay, and so what we'll see a lot of times is like these are. I've never heard of Cermets, C-E-R. Metal matrix composites with ceramic particles embedded in high volume fractions. We also see the rubber matrix with carbon black, so just carbon particles. That's another very common one. We use that in tires. It really reinforces the rubber that we have cross-linked. So these particle reinforcements, they're much, this would be for whiskers too, are just like particles. We're going to treat them just like particles. So some ceramics and things, they form fibers better than particle, or at least you can get these little bitty fibers out easier, and so we'll reinforce them with either short fibers or particles. And so the stress, the way that works is just a little bit different. So now if you think about it, we're loading this way. So we're loading this in this direction, in like the transverse direction, and so our springs would be in parallel. That's kind of the way to think about the stiffness here. And so this is how you calculate the stiffness of the composite for a particle or transverse direction loaded fiber reinforcement. Or either a particle composite or a whisker composite, or the fibers loaded in the transverse direction. So this is how you calculate the stiffness using this equation. And so what we find, if we're looking at, so here's modulus versus volume percent. So this is the upper bound. The green is the best we could get in terms of stiffness, and blue is the worst that we get in terms of stiffness. And so the composite, if you check the stiffness in all these different directions, it'll lie within that envelope. Because, of course, we don't always get them completely aligned longitudinally. Another important point here, you know, we can engineer other properties other than mechanical properties. We can engineer conductivity for electrical and thermal purposes, so we can increase the electrical conductivity of something by reinforcing it, compositing it with something else. Same thing for thermal conductivity. You can actually get some thermally conductive like polymers and electrically conductive polymers like that. Polymer matrix. Okay. So the three different, this is important. So this is one of those things I would want you to know by the end of the semester. What are the main goals for the three different types of three different types of composites? With ceramic composites, if we have a ceramic matrix, we're trying to improve the toughness, specifically the fracture toughness. With polymer matrix composites, we're trying to improve the stiffness and strength, either one of those. There's a bigger improvement on stiffness, but strength definitely improves. And then with metal matrix composites, we're looking to improve the creep resistance. What do you think the reinforcement is in ceramic matrix composites? Take a quick poll. Yeah. Okay. Let's make one real quick. Do you guys think that ceramics, metals, or polymers? We're trying to improve the fracture toughness. Okay. Okay. Some of you have read the book. Okay, so it's actually ceramics. Ceramics reinforce ceramic matrix composites usually. And it's really interesting the way it there. Ceramic matrix composites. What they do is it's called transformation toughening. I wanted to get to this, and we won't get through all the slides, so some of it just won't be covered. What'd you say? Not talking. Okay. So ceramics are used to reinforce ceramic matrix composites. And what happens is that stress is like an energy. So you think of at the crack tip, there's this stress concentration. So normally that's going to lead to fracture. When we talk about like the fibers being able to bridge, you know, a fiber or a compressive force at the surface wanting to close that crack, well, basically in the presence of that stress, we have these particles the reinforcing particles will transform. So just like when we heat something up, you know, heating something up is one way of getting it to change, to put energy into a material. And so when we heated up iron, it would have its phase transformation. It has another form it wants to have. So that'll happen with these zirconia particles. And the presence of that stress, you put energy into the composite, they'll transform from a tetragonal phase, which to a monoclinic. And they increase in volume. The volume increases. So we're stuffing more people into the elevator now, and it puts a compressive force at that crack tip that closes the crack tip. These are actually becoming, it's fairly new in composite world in terms of how much they're used. But I was talking with somebody from GE. They're starting to use these for ball bearings, or looking at using them for ball bearings, doing research on that. And they're getting tons more wear resistance from them. But of course, they couldn't do that before because within these engine components, they need a lot of, a long life. They don't want to have to replace. They're never going to replace them. And so so previously, all that fracture and then compressive and of the ceramics, the low fracture toughness would keep us from being able to use them. Okay, so another point here, the stress-strain curve ends up somewhere between the two. So again, we're going to end up somewhere between the two, and we have a pretty sudden failure point because once the fibers fail, they're not bearing the load anymore. Then we've at that point when the fibers stop bearing any load, we've immediately overstressed the matrix. So here we're above the failure stress of the matrix. So as soon as the fibers aren't able to bear anything, it's a brittle fracture. So actually there was a video where some people from Boeing, I'm trying to remember which airplane, were showing having somebody come and take a hammer and try to dent their carbon fiber panel, showing how great and strong it was. But it's actually not, it's not dentable. It's not really, when they fail, when they actually break, it's more like a brittle fracture of them, often. Another way we can have composites is, this is what I was talking about, these sheets. They'll have longitudinal sheets that way, and and just vary it, and so you get really great properties within the sheet. Now, why would they go to the effort of making this longitudinal like that, instead of just allowing them to be in any direction? This actually is better, because we get that, when we have that stress, we're getting the best stress on half of the sheets in this direction, and the best stress on half of the sheets in this direction. So that's how they do a lot of those carbon fiber reinforced panels, by stacking things like that. Now, sandwich panels, this is another interesting thing. So why do we use these? What's really great about sandwich panels? What mechanical property do you like them for? They're low density. They're very stiff, right? If you think about using this, you'd use it in something where it might be a bending load. They're very stiff. They're very resistant to bending. And so what's great about these is the density is all concentrated on the outside. And we just have this here with a honeycomb structure. Another thing we'll use them for is insulating panels that need some kind of structure to them. So if you think about it, like the cheap little styrofoam coolers you get at Giant Eagle, what's the big difference between those and, say, like a real cooler, like an igloo cooler? They're about the same. The igloo cooler might have air inside of it instead of a foam. But the big difference is one's coated with plastic. I mean, effectively, they're both trying to make use of the thermal properties of air, the thermal insulation of air, either with the added structure of the styrofoam or not. But the igloo one, we have the face sheet. We have this covering that can bear more load and is more durable. So foams in general we can make them from anything. So we think of foams as being a polymer foam. But these ones are made from the bulk metallic glass. And so the whole point of that is we get the structural components of the metallic glass, which is a very, very strong material, but we get the lightness of the foam. So foams in general, any foam, gas is like the matrix space. That's kind of matrix is usually it's holding it all together, but in this case, gas is like the matrix. And then the material is like the reinforcement, giving the structure to it. So what we're really trying to do is take the thermal and insulation of gas and the lightness of gas and reinforce it with some kind of structural backbone. Okay, so let's think about this. Sorry? It should be. Right there, text that one. The very first one? The very first question, top hat monocle, you mean? I don't think I understand your question. Okay, good. So again, toughness is what? It's the area under that stress strain curve. So when we looked back at that, if there's the ceramic, there's the metal, our composite's somewhere in here, so we're still not as tough as the metal. There's still less area under that stress strain curve. So even the toughness is somewhere in between, because the other two properties are in between. Okay, so what do we reinforce? What are some of the most common polymers? Glass fiber is one of the most common because it's not as expensive as the carbon fibers, obviously. Typically use e-glass, which is a mixture of other things added to silica. And it's got some good properties for the e-glass. And then we'll use thermosets in the matrix. So these are, not as great of properties as a carbon fiber, but they're used a lot more. So again, in like the boats, you see the fiber composite sport boats and things like that. The carbon fiber, so this is supposed to be a C. So the carbon fiber reinforced are much stronger. So if you look at the difference in the modulus here. That's an incredibly high modulus. Again, because the carbon-carbon bond is the strongest bond that we have. You know, that's where carbon and diamond. These carbon fibers and diamond. So the same applications, but when we're willing to pay a little more for that extra strength. So some of these actually at high enough volume fractions, we can use them at higher temperatures, even though they've got a polymer matrix. Another thing we can do is change the winding. You know, if you think about these epoxies, they're pretty viscous at their temperatures, and then we cure them to set them, you know, form those cross links. And so the fibers are fed through the resin and then wound, and then they cure it. And they've got, what's great about this is we can get some really, you know, depending on how a pipe or a component is going to be loaded, we'll get different, you know, great properties for a certain thing. So for pressure vessels, where we know we've got a hoop stress, you can do this with, you know, more circular pressure vessels too. So they'll use carbon fiber reinforced composites on like brake pressure vessels for brakes, things like that. Okay, the summary. Composites, we're going to get properties somewhere in between. So what do I want you to know about composites for the rest of your life? We make composites to deal with the bad things of the matrices in general. So again, that's why metal matrix composites, the big problem with metals is their density and creep performance. That's why we make ceramics. We improve the creep performance, and usually we're reinforcing the metal face with some kind of ceramic particle that's lower in density. The ceramic matrix composites, we're looking to enhance the fracture toughness, so make them able to actually withstand some cracks. Polymer matrix composite, we're trying to make them stiffer and stronger. Polymers are great, but they're great light, great cost usually, but they have almost no stiffness or strength compared to the other two. I want you to know the three main types: the fiber reinforced, particulate, and then the structural. We didn't really talk much about structural, but you know, these sandwich panels is the word I was looking for. And polymers are, you know, very ubiquitous. They're used a lot in a lot of different applications. And the big thing here, we can estimate the elastic modulus in both, but really the tensile strength we can only really look at for those longitudinal fibers very easily. And then, are they isotropic or anisotropic? And for the fiber, they could be isotropic, right? As long as the fibers. So one of the questions on the finals in past years has been, you know, for a certain class of group of potential materials, which ones might be isotropic or anisotropic? So when we're talking about composites, they are isotropic if the matrix is isotropic and they're particle reinforced with a random, you know, an even random distribution, or short whiskers. So if the matrix itself is isotropic and the reinforcement is isotropic in its dispersion and geometry. And so, you know, that's kind of the way to think about it. So single crystals definitely aren't isotropic. What else is, how could we make like a polycrystalline steel be anisotropic? Still polycrystalline. cold work it one way. So, you know, if you think about if we've got a cold worked metal or something, or a drawn polymer, it's no longer isotropic.